Welcome to this next video in the playlist on group theory. In this video, what we're going to talk about is internal and external direct products. Now, in order to understand the concepts that we're going to see in this video, you need to have watched two videos that are previous in this playlist on group theory, namely the video on the product of two groups, which will be way back at the beginning of the playlist on group theory, and then the second video that you need to have watched is the product of two subgroups, a video on the product of two subgroups, and that will be further along in the playlist on group theory. Okay, I'm going to review the material from those two videos right at the beginning here, because it is utterly essential that we understand those concepts, namely the concept of the direct product of two groups and the product of two subgroups. Okay, in order for us to understand what is meant by the internal and external direct products, which are just those very concepts applied under certain circumstances. Okay, right. So let's begin by recapping what is meant by the direct product of two groups. Okay, so remember, the direct product is a way of building a third, larger group from two groups. Okay, so if you have two groups, which we'll call capital G1 and capital G2, so I'll just jot these down here. So let's say we have capital G1 as one of our groups and capital G2 as our other group. And remember, these are just sets of symbols with composition laws defined on them. We'll denote everything to do with group 1 in orange, and we'll denote everything to do with group 2 in red here. Okay, so we have these two groups, G1 and G2, and what we now want to do is construct a larger third group from those two. Okay, and one way of doing that is direct producting the two together. Okay, and this is written like so, G1 cross G2. Okay, now often, indeed in the video on the product of two groups, we just called this the product of the two groups. Its full name is called the direct product of the two groups. Okay, so we can product the two groups together in this way. We can take G1 cross G2, and what we're going to form is a new group, a third, larger group. Now, of course, any group consists of a set with a composition law defined on it. So firstly, to construct this thing, I need to tell you what the set is, and then I need to tell you what the composition law is going to be. Okay, so let me firstly remind you what the set is going to be. So the set, remember, consists of the Cartesian product of these the sets that underlie these two groups, hence why the symbol here is exactly the same symbol as you would use for the Cartesian product of two sets. Okay, so the set will consist of all ordered pairs, little g1, little g2, where little g1 is an element from capital G1, and little g2 is an element from capital G2. Okay, so G1 cross G2 as a set is just the set of all ordered pairs of an element from capital G1 with an element from capital G2. So to utterly stress what you're doing here, you would have to take every possible ordered pair, everything of this structure. Okay, so you put every possible little g1 from capital G1 in slot number 1, and for every single one of those you'd put in every single possible little g2 from capital G2 in slot 2 here, and you take every possible combination, every possible pair here, you put them all into a great big set, and that is the set on which we are going to define the composition law to turn it into a group. This is the set that will underlie this third new group that we are forming from the two original ones, which we're calling the direct product of the group capital G1 with capital G2, or G1 cross G2 here. Okay, so now of course what we need to do is define a composition law on here. Okay, and the way we define composition is component-wise. So let's say I've got one ordered pair here, G1, G2, and let's say I've got a second ordered pair here, G1, let's say bar, G2 bar. Okay, so of course we've got a different entry potentially in our first slot and a potentially different entry in our second slot. Of course they don't have to be different entries, but more generally they will be. Okay, you could compose the same element with itself. Okay, but more generally G1 bar will not be the same as G1, and G2 bar will not be the same as G2. Okay, so just to put this down, G1 and G1 bar are just arbitrary elements of capital G1, and G2 and G2 bar are just arbitrary elements of capital G2. Okay, and now what we're going to do is define the composition of these two ordered pairs here. Okay, so this composition symbol, this will be composition in the direct product, which is why I'm underlining it here, well, colouring it in here in pink. I'm colouring everything to do with the actual new group that we're forming here, the direct product of the two groups G1 and G2 in pink. So this is composition of elements in this set, composition in the direct product group, okay, and therefore I will colour it in pink. Okay, and the way that this is going to be defined is component-wise, like so. Okay, so what you will do is you will compose G1 and G1 bar together according to the composition law on capital G1. So you'll compose G1 with G1 bar, and that composition will be in capital G1, so I'll colour it in orange. And you'll compose G2 with G2 bar, and that composition will be in capital G2. Okay, so I will colour that in red here, because I've vowed to colour everything to do with the first group in orange, and everything to do with the second group in red. Okay, so really simple way of defining it. I mean, how else would you define it? Okay, this is the most common sense way of defining it you could possibly come up with. Okay, just compose these two entries together, which we know how to do because they're both elements of the group capital G1, and compose these two elements together because they're both elements of the group capital G2, and look what you get here. G1 composed with G1 bar, that's just going to be some element of capital G1, because G1 is a group and therefore closed. G2 composed with G2 bar, that's just going to be some element of capital G2, again because capital G2 is closed. So look, we end up with another ordered pair in our set here. So this is a beautiful closed composition law. So what you could now imagine doing is drawing out a great big table with all of the ordered pairs given a row and all of the ordered pairs given a column, and you could use this law that I have defined here to work out every single one of the entries in that composition table. Okay, and the composition table that you will get along with this set does indeed obey the axioms of a group, and we prove that in the video on the product of two groups, and I won't repeat that proof here, but there's a basic reminder of how to actually build the direct product of two groups. Okay, so that is what is meant by the direct product of two groups, and these two groups don't need to be related to one another at all. G1 and G2 can have totally different elements and they can look totally different, and you can always still form the direct product of the two. Okay, they don't need to be related whatsoever. Right, contrast that now to the product of two subgroups, which I'll just call the subgroup product, and this is the other topic that's going to be utterly essential to understand internal and external direct products. Okay, so this is covered in a different video from this one, titled a very similar thing. The video on direct products is entitled The Product of Two Groups. The video on subgroup products is titled The Product of Two Subgroups, and it's much further on in the playlist on group theory. I consider it a much more advanced topic. Right, okay, so here the two things that we're going to product together must be subgroups of some larger group. Okay, so you'll have H and K, okay, capital H and capital K, which are going to be subgroups of some group capital G. Okay, so just drawing a little picture here, you'll be working in some much bigger group, capital G here, and you'll have two subgroups of it. So here's one, let's say H, and here's another, here's K, and of course they have a non-empty intersection, because whenever you intersect two subgroups together, we know we always get another subgroup back. So here is G coloured in red, and then we'll have H here outlined in green, and then finally K here outlined in orange. Okay, right, so we have these two subgroups of some larger group. What we can now do is define a product of them, and again it's a very intuitive definition, but this time the product that you get is not necessarily a group. Of course, the interesting case is when it does end up as a subgroup of G, i.e. a group, but it doesn't in the general case. Okay, so what you can now do is product H and K together, and the way we define this is initially just as a subset of G, and it's the subset that contains all elements of the form little h composed with little k, where little h is an element of capital H and little k is an element of capital K. Okay, now clearly this is going to be a subset of capital G, because what are we doing here? I'm taking loads of elements from capital H. In fact, I'm going through every element of capital H here. So I'll just underline everything to do with capital H in green here. I'm going through every single element of capital H, and I'm saying for every element of capital H, what I want you to do is compose it with every single element of capital K, every little k that's in capital K. Take all of these compositions, all of them are going to be answers in capital G, because fundamentally all of these elements, little h and little k, are in capital G, so you're just composing two elements of capital G together, so you'll get another element in capital G together. G back as the answer. Okay, so this will end up always as a subset of capital G. Okay, and in general that's all you can say. Of course, we're interested in a special case where this ends up as actually being a subgroup of capital G, where you're producting two subgroups together to get another subgroup of capital G. And what we prove in the video on the product of two subgroups is that the condition for that to be true is, okay, I'll write it out here, the product of the two subgroups H and K will be a subgroup of capital G if and only if I utter the equivalent statement, if and only if the product HK is equal to the product KH. Okay, now let me explain or remind you of exactly what that actually means, and I'll just move this piece of paper up. Okay, so these two products are not necessarily the same thing. The product of H with K is, remember, as we've got defined up here, the subset that contains all things of the form little h composed with little k, okay, where little h is an element of capital H and little k is an element of capital K, okay, whereas the subgroup product of capital K with capital H, this is the subset of capital G that consists of all things little k composed with little h, where little k is an element of capital K and little h, of course, is an element of capital H. Now, those two subsets are not necessarily going to be the same thing. Of course, if we're working in a larger group, capital G, that is abelian, if G is abelian, then obviously these two subsets are going to be exactly the same thing, because in that case, little h composed with little k will equal little k composed with little h. So all of the products here will correspond to the opposite product in the other one. Okay, they'll give the same answer in the group capital G, but in general, in a non-abelian group, you cannot instantly say that these two subsets are going to be the same thing. However, what we do prove in the video on the product of two subgroups is that the product HK being a subgroup of G occurs if and only if it's equivalent to saying that these two subsets are the same thing. So if these two subsets are the same thing, it implies that the product of the the product, either way round you can have it, but we've got it this way round, H with K is going to be a subgroup of capital G. And the only way for this to be a subgroup of capital G is if this is true. Okay, right. Then the final thing that we do in the video on the product of two subgroups is we give a condition for this to be true. Okay, we show that if either of the two subgroups normalizes the other, okay, so if either H is contained within the normalizer of K and G, or K is contained within the normalizer of H and G, then that implies that this is true, and therefore it implies that the product will be a subgroup. Okay, so one of the ways that you can ensure this is true is if either H is a subgroup of the normalizer of K in G, or if K is a subgroup of the normalizer of H in G. Okay? Right, so that's a way in which, so if either of these is true, it will imply that this is true, and therefore that the product of the two, the subgroup product of the two, is actually a subgroup of capital G. Okay, right, so again, I can't go through all the proofs of these things, because it takes quite a bit of time. Okay, so I refer you to the video on the product of two subgroups if you wish to see the proofs of these statements. Okay, so there's the brief reminder portion on the concept of the direct product of two groups and the product of two subgroups. And of course, as I pointed out at the end of the reminder on the direct product of two groups, the two groups didn't need to have anything to do with one another in that case. In the case of a subgroup product, they do need to have something to do with each other. They both have to be a subgroup of some larger group. You have to be able to think of these two groups here, H and K, that you are producting, as lying within some larger group which contains both of them. Okay, that didn't need to be the case for the direct product. You didn't need to be able to think of G1 and G2 as being contained in some larger group that contains both of them. Okay, right, so now time to actually tell you about what the internal and external direct products are. Well, the external direct product is just the direct product under a certain circumstance, and the internal direct product is just another name for a subgroup product under a special circumstance. Okay, so we just rename these concepts in a certain circumstance. So let me now outline what this special case is, where we use different names for these same concepts. But in essence, if you understand these two concepts, you understand already what the internal and external direct products are. It's just different terminology that we use in certain special cases when we're applying these concepts. Okay, and the special case is that we have two subgroups of a certain group that are both normal subgroups. So let's say we have H and K, which are both normal subgroups of capital G. Okay, so we have two subgroups that are normal subgroups inside of capital G, and the intersection of these two is equal to the trivial subgroup. So if I intersect these two normal subgroups together, I get the trivial subgroup. So drawing a picture here, let's say that this box here represents the group capital G. Okay, so I'll outline it in red again here. Okay, now what we're going to have, the special case that we're going to have, is we're going to have two subgroups, H and K, and their intersection is going to be tiny. The intersection here, H intersect K, must be the trivial subgroup. It must just contain the identity element of the group. So this little blob in orange here just contains the identity element. Okay, so let's say this one here is H, and this one here is K. Okay, and they're both normal subgroups in G. Okay, right. So now, what can you do with these two subgroups? Well, of course, what you can do is you can take the subgroup product of the two. Okay, and this will end up being a subgroup of capital G. The reason is that they're both normal subgroups of G. Okay, so in this case, the normalizer of K in G is going to be the entire group. So the normalizer of K and G is the entire group. Whenever you've got a normal subgroup, then its normalizer, the subgroup of the group of elements which normalize K, i.e. when they're used to conjugate K, give K back again, is of course the entire group, and the same for H. So the normalizer of H in G is equal to the entire group. Okay, so clearly here, H will be contained within the normalizer of K in G, and K will be contained within the normalizer of H in G. Okay, so in fact both of these are satisfied, so certainly it is true that this is true, i.e. the product of H with K is the product of K with H, and therefore indeed the product of H with K does form a subgroup of G. So you can take the subgroup product of these two normal subgroups and you can be absolutely sure that you're going to get a subgroup of capital G. Now in this case, this subgroup product of these two normal subgroups of G which have trivial intersection, this is called the internal direct product. Okay, so we rename the subgroup product, we give it this fancy title, the internal direct product. Okay, and if you're wondering why is it being called a direct product, okay, why is it being compared to the direct product here, the answer will come very shortly. Just wait a moment, you will find out why this is called the internal direct product, you will see that. Okay, so in this special circumstance where you are taking two subgroups that are normal subgroups and subgroup producting them, and also their intersection is equal to the trivial subgroup, you call the subgroup product by this bigger, better name, which is the internal direct product. In addition, what you can consider doing is direct producting H with K. Okay, these are, after all, two groups in their own rights. I know that they are both subgroups, both normal subgroups of the group capital G, of this larger group, but they are, after all, groups in their own right. If you get rid of all of the portion of G that's outside of each of them, they exist in their own right. They don't need the larger group capital G to exist. Okay, they can exist in their own right, so they can now be producted as two groups in their own right in the direct product manner. Okay, and of course what you will do is you'll construct the set of all ordered pairs of elements from capital H with capital K. I'll just spell this out here. So you'll have the set of all ordered pairs, little h, little k, where little h is an element of capital H and little k is an element of capital K, and you'll define a composition law on that set, which will just be component-wise as we've described. Okay, now in this special case, you give this the new title, the external direct product. So rather than just calling it the direct product of these two subgroups that are normal in G with trivial intersection, you call it the external direct product. So in this special case where you are direct producting two subgroups that are normal inside a larger group capital G and which have trivial intersection, you call that direct product the external direct product rather than the direct product. So that's what I meant by these are not new concepts, they are just the same old concepts that we learned long ago applied in this special case. Now, why have we called the subgroup product the internal direct product, suggesting it has something to do with the external direct product, which is the real direct product here? Well, the answer is that these two things that you get, the internal direct product of H and K and the external direct product, they end up being isomorphic. They end up being the same thing, effectively. Different symbols, different notation, but of course that's not real, that's just man-made. Okay, the algebraic structure, the true meaning, the true thing that we're studying, the symbols are meaningless, those are the same between these two. They are isomorphic to one another. Okay, so under this special circumstance where you are taking the subgroup product of two subgroups that are normal in G with trivial intersection, then if you take that subgroup product, it ends up being isomorphic to what you'd get if you direct producted the two subgroups together, and that's the reason that we call the subgroup product in this case the internal direct product, and we call the direct product in this case the external direct product, because effectively they're giving the same thing, but these two different approaches of getting it. One is considered the external way of getting it, where you're thinking of these two things as being external to the group capital G, i.e. you don't need to think of them inside of this larger group capital G in order to be able to do this one. And this one's the internal one, where to define this you did need to think of them as being inside, internal to this larger group capital G. So that's where this notation or these names come from. Okay, so we'll have a break here, and in the next video, of course, what I will do is prove that this statement is true. Prove that in this special case where H and K are normal subgroups inside of G with trivial intersection, then the subgroup product, or the internal direct product, as it's called here, is going to be isomorphic to the external direct product, or the true direct product.